Hello everyone and welcome. Think of me as your mentor, and today we're going to dive into the absolute most colorful chapter in your Class 10 science syllabus, the human eye and the colorful world. We are saying a massive goodbye to boring rote memorization today because we're going to visually unpack every single concept so you can confidently score full marks on your board exams. So let's jump right in, shall we?
Here's our roadmap for today. We'll cover 5 major topics. First, the human eye explained. Second, vision defects and corrections. Third, prisms, dispersion, and rainbows. Fourth, atmospheric refraction unlocked. And finally, scattering of light explained. By the end of this single session, your entire chapter will be completely revised, and I'll even be dropping exact exam tricks and NCERT keywords that examiners absolutely look for.
All right, let's kick things off with our first section, the human eye explained, the anatomy of vision. You know, our eye is basically nature's ultimate camera. Let's see how it actually captures this beautiful, colorful world around us. Let's break down the anatomy. The outermost, transparent part is the cornea. That's where light first enters. Right behind it, we have the iris and the pupil. Now listen closely, because a very common mistake students make is confusing the functions of the iris and the pupil. In simple terms, the pupil is just that black opening that lets light inside. The iris is the actual muscle that controls the pupil. It shrinks the pupil in bright light and expands it in dim light to manage exactly how much light gets through. Then comes our crystalline lens, which takes that light and focuses it onto a screen at the back of our eye, which we call the retina. Moving on to an absolutely crucial concept, the power of accommodation. Unlike a glass camera lens, our eye's lens is actually made of a flexible, jelly-like material, and it's controlled by these things called ciliary muscles. When you're looking at a mountain way off in the distance, your ciliary muscles relax, making the lens thin. But when you're reading a book up close, those muscles contract and the lens becomes thick. This amazing superpower to adjust the focal length on the fly, that is exactly what we call the power of accommodation. Okay, time for a board exam cheat sheet. You absolutely need to remember these exact facts for your multiple choice questions. For a normal eye, the near point is exactly 25 centimeters. Bring a book closer than that, and it gets blurry. The far point is literally infinity. That's why we can see stars that are light years away. Also remember, the image formed on the retina is always real and inverted, meaning it's upside down. Our brain does the heavy lifting to flip it right side up. And finally, persistence of vision is 1/16 of a second. This just means an image stays registered on our eye for a tiny fraction of a second after we see it. But what happens when this natural camera stops working perfectly? Well, don't worry. Physics has a solution for pretty much everything. Let's move on to Section 2, Vision Defects and Corrections, Fixing the Blur. The first common defect is myopia, which is also known as nearsightedness. With this, you can see nearby objects perfectly clearly, but things far away get completely blurry. Notice how the eyeball has actually become a bit too elongated, or the lens is too thick, which causes the image to form in front of the retina, falling short of the screen. To fix this, we use a concave lens. This lens slightly spreads out the light rays before they enter the eye, pushing the image perfectly back onto the retina. Now, the exact opposite of that is hypermetropia, or farsightedness. Here, you can see distant objects just fine, but reading a book up close is a real struggle. In this case, the eyeball is too short, so the image gets pushed right behind the retina. To correct this, we need the light rays to converge sooner. The perfect solution? A convex lens. It pre-bends the light, pulling the focus right back where it belongs. As people get older, 2 other very common problems can pop up, and you definitely need to know the difference between them. First is presbyopia. This happens when the ciliary muscles naturally weaken with age, making it hard to focus on near objects. We fix this using bifocal lenses, concave on top, convex on the bottom. But cataract is something entirely different. That's when the eye's natural lens actually becomes milky or cloudy, and the only way to fix a cataract is through surgery. Here's your cheat sheet for vision defects. Examiners love asking for the causes, so lock this in. Myopia is caused by an elongated eyeball or excessive lens curvature, while hypermetropia is caused by a short eyeball or a thin lens. And here is my biggest pro tip for you. Always, always draw arrows on your ray diagrams. Without those arrows showing the direction of light, you will absolutely lose easy marks. Oh, and if you get a question saying, a student in the back row cannot read the board, boom, you instantly know the answer is myopia, and the fix is a concave lens. All right, we've seen how the inside of the eye works.
Now let's turn our gaze outwards and look at the magic of light itself. Welcome to Section 3, Prisms, Dispersion, and Rainbows, Playing with Colors.
Sir Isaac Newton actually made a completely mind-blowing discovery. He found that when a beam of white sunlight passes through a glass prism, it physically splits into its 7 component colors. Vibjor. This splitting effect is called dispersion. Keep in mind, red bends the least while violet bends the most. Why? Because different colors actually travel at slightly different speeds when moving through glass.
So how exactly does that beautiful rainbow form up in the sky? Well, after it rains, every single tiny water droplet hanging in the air acts like a miniature prism. It happens in 3 exact steps. At point A, sunlight enters the droplet, refracting and dispersing. Then at point B, the light hits the back of the drop and bounces inside. This is called internal reflection. Finally, at point C, it exits back into the air, refracting one last time to shoot that gorgeous spectrum of colors right into our eyes. Let's lock in some high-scoring tips for prisms and rainbows. When explaining rainbow formation, a lot of students make a huge mistake. According to NCERT guidelines, you must use the term internal reflection on your answer sheet, not total internal reflection. Please remember that. And also, always note that a rainbow will only ever form in the direction completely opposite to the sun. The sun literally has to be at your back for you to see it. We've mastered the ground-level phenomena. Now let's look up at the massive ocean of air right above our heads, the atmosphere. Let's dive into Section 4. Atmospheric Refraction Unlocked, Nature's Illusions.
Now, I want to ask you one of the most classic, all-time favorite questions of board examiners. Why do stars twinkle, but planets do not? This is something that confuses almost everyone, but today we're going to clear that doubt forever. Here's the secret. Stars are so incredibly far away that they act as a single tiny dot, or a point source of light. As that starlight enters Earth's atmosphere, it crashes through different layers of air with constantly changing densities. This continuously bends or refracts the light. Because of this shifting refraction, the star's apparent position slightly changes, and the amount of light hitting our eyes fluctuates. And that right there is what causes the twinkling effect. And because of this exact same atmospheric bending, we get to witness a daily magic trick. We actually see the sun 2 whole minutes before it technically rises and 2 minutes after it physically sets. Why? Because the light from below the horizon gets bent upwards by the Earth's atmosphere. Basically, the atmosphere gives us about 4 extra minutes of daylight every single day. So, going back to our question, why don't planets twinkle? The magic keyword you need for your exam is extended sources. Planets are much closer to Earth, so they act like a massive collection of point sources. If the light from one point dips, the light from another point increases, essentially canceling out or nullifying the twinkle effect. Make absolutely sure you write extended sources in your exam to get those 2 marks.
And now, we've reached the final act of this amazing, colorful chapter. I want you to imagine light crashing into millions of tiny dust particles and gas molecules. Let's move on to Section 5, Scattering of Light Explained, Painting the Sky.
Students often lose easy MCQ marks because they mix up refraction and scattering. So I want you to memorize this breakdown. If light is bending as it travels through changing layers of air, that's atmospheric refraction, like twinkling stars. But if light is physically crashing into a particle and bouncing off in all directions, which is the Tyndall Effect, that's scattering of light. That's what gives us our blue sky. Keep them separate and you're golden.
There are 3 golden rules of scattering you absolutely need to know. Rule 1, fine tiny air molecules are great at scattering shorter wavelengths, like blue light. That's exactly why the daytime sky is blue. Rule 2, larger particles scatter longer wavelengths, like red. Rule 3, the water droplets in clouds are huge. Because they're so large, they scatter all colors equally, and when you mix all the colors of light together, you get white light. That's why clouds look white.
All right, time for our final set of high-scoring tips. Why does the sun look red at sunrise and sunset? Well, at those times, the sun is low on the horizon. The light has to travel a super long distance through the atmosphere. Almost all the blue light scatters away during the journey, and only the longest wavelength, red, manages to survive and reach our eyes. Conversely, at noon, the sun is straight overhead, the distance is short, so very little blue scatters, and the sun appears white. Just remember, wavelength is inversely proportional to scattering.
We started our journey inside the tiny lens of the human eye, and we've traveled all the way out to the vast sky. Before we wrap up, I want to leave you with a thought-provoking question. If the Earth had absolutely no atmosphere, no air, no dust, nothing, what color would the daytime sky be? The answer is completely black, because without particles in the air, there would be no scattering of light whatsoever, which is exactly what astronauts see out in space. I really hope this session made the chapter fun, visual, and easy to understand. Keep learning, stay curious, and go absolutely crush those board exams. Best of luck!